The talk by Susan Friedlander of USC, and her official title is Instabilities and Ill-posedness for the magnetogeostrophic equation, and her more informal title is given up there. And as far as I understand, this is work that you've done jointly with Vlad Vikol, your graduate student, former graduate student.
Turn on the microphone, I hope. Is it on?
Yes.
Yes, good. So thank the organizers very much for the invitation to speak here, which is a great pleasure. I think the first time I came was at a workshop that Keith organized in 1992. Am I remembering that correctly? On dynamo theory. There are still some of the same old faces, but a lot of new faces. It's an interesting area with a great history partly due to Keith. So what I'm going to talk about then is a particular active scalar equation, which was presented as a model, a possible sort of simplistic model for the geodynamo in a paper of Keith. And the work that I'm discussing is all joint with Vlad Vikol, former graduate student at USC, currently a postdoc at the University of Chicago, and about to move to Princeton, where he will be an assistant professor. What are we talking about? Well, the geodynamo is the issue of the generation and sustenance of a magnetic field due to the motion of the electrically conducting fluid that makes up, or at least is assumed to make up, the Earth's fluid core. If we look at the full system to describe this problem, it is the system of rotating, convecting, electrically conducting fluid. So we have MHD to consider. This system is, of course, highly complex and from an analytic point of view, very difficult. From a numerical point of view, also very difficult to handle. So often one considers a simpler model, and one particular model which was suggested by Keith, I think actually first of all in a paper with David Loper, and then more recently in a paper that appeared in 2008 in an IUTAM proceedings. So in this model he has ignored or argued why certain terms in the full system could be eliminated or ignored from the point of view of scaling analysis in the Earth's fluid core. So what is left from that full system of rotating, convecting, electrically conducting MHD are the following equations. So here we have basically the equation of motion, the equation for the evolution of the velocity field, and as you can see, the nonlinear terms have disappeared. The problem is written in the rotating coordinate system, so we have Coriolis force. So dominant balance is between Coriolis force, the pressure. Here the pressure is the combination of the magnetic pressure and the fluid pressure, and then what comes up is left over from the Lorentz force, and here is the contribution from gravity. Theta stands for the perturbation buoyancy, or one can think of it as temperature density or density, but we're referring to it as buoyancy. Then the magnetic induction equation, what remains of the magnetic induction equation, sits here. We're assuming that the fluid is incompressible, the divergence of U is equal to 0, and the divergence of B is equal to 0, B being the magnetic field. So this system of equations forms a linear system, which is something that's rather nice. Keith, in his paper in 2008, puts back the partial with respect to T of the magnetic field B, although Keith observes that it is mildly inconsistent to retain that term and yet to have eliminated the other terms that come basically from the evolution in these two equations. What we're going to do, though, is not put that term back, but to be consistent with the scaling where those terms have been removed, but consider this system, which doesn't involve a partial d by dt, but is a linear system in the variables b, u, and theta. The only nonlinearity we will be retaining is in the evolution equation for the buoyancy field theta. Now, this equation, of course, is nonlinear because u is related to theta via this system. So we have here a nonlinear evolution equation, and the equation contains a term involving the diffusivity. Kappa we can think of as the coefficient of diffusivity, and we have a Laplacian term, and a source term, which will be actually the term that is generating the whole motion. The source term possibly coming from latent heat of solidification. It comes from an appropriate physics in the core. So the source term we will assume is specified. This is the term for the evolution of the buoyancy theta, coupled with this linear system for the vectors b and u. So now, to go to the back of Keith's paper, rather than the beginning of Keith's paper, in the back of Keith's paper he writes, in the context basically of this active scalar equation, which I've rewritten here, he writes that quite apart from the geomagnetic context considered above, there's an interesting general class of problems here that calls for investigation by direct numerical simulation. This equation with u coming from the system that I showed you before is in some respects similar to Berger's equation, but has a clearer physical basis. The velocity field u as a function of theta can here be chosen to be fully three-dimensional. The quadratic nonlinearity is similar to that of the Navier-Stokes equations, but here we're dealing with a simpler problem of a scalar field evolution, and the complications associated with the pressure are absent. These features alone suggest that the problem deserves numerical investigation. Perhaps someone at this meeting will be induced to take up the challenge. Well, we took up the challenge, but we took up the challenge not really from a numerical investigation, but an investigation of the analysis of the PDE. And that's what I'd like to discuss. So now, since we want to basically investigate the analytic properties of this equation, we further simplify the problem. Instead of looking at it as one should in the geodynamo context, in an equation in a spherical shell, basically a thick spherical shell, we've vastly simplified the geometry of the problem by considering the problem on basically a tangent plane. Here we have the axis of rotation. We're going to align gravity with the axis of rotation, and we're going to consider the ambient magnetic field, which is stationary and, according in Keith's assumption, uniformly constant. We're going to consider a very particular choice of the base magnetic field, which lies in the horizontal plane. So that we will be retaining the essential features of this equation, which are written here. Mainly the really important feature is the nonlinearity, but simplifying the notation somewhat with this assumption. So now these equations which were in red, as we say, can be manipulated just using standard vector manipulation to write u and b as differential operators on theta. And when we do that, we obtain the following. So here, u, which we think of as 3 dimensions for the physical problem, it's a 3-component vector. Each component is an operator acting on theta. And similarly, for the magnetic field b, we've got a 3-dimensional vector. Each component is now this times an operator acting on theta. So the issue really is in the structure of this operator. And what does the operator look like? Well, here, rather than writing it down in terms of the derivatives, I've written it down in terms of its explicit Fourier multiplier symbols for the operator. So here are the 3 components of the symbols written as functions of the Fourier vector k, m1, m2, and m3 in our 3-dimensional problem. So some things to observe about these symbols. First of all, they're highly anisotropic with respect to K1, K2, and K3. And this is to be expected because the physical problem has 3 forces acting: the Coriolis force due to rotation, the Lorentz force due to the base magnetic field, and then gravity. So those 3 forces are giving reflecting the anisotropy of the problem that K1, K2, and K3 all occur in different ways. Something else about the operator that is very interesting is that these operators are even with respect to interchanging the vector k with the vector minus k. Even operators in fluid dynamics are or even symbols are less common than odd symbols and have some important implications for the properties of this equation. For another example of an even operator is the equation that comes from the porous media equation. That's an even operator, but odd operators are actually more usual. But even operators are quite interesting, as I hope I will convince you. Now, another feature of this is, okay, what's the order of these operators? Here, we've got a denominator term that I've written here, and now we're going to be considering this evolution equation for functions, and for simplicity, we're going to look at periodic functions, so we're going to be working in a 2 pi cube, or Z3, 3 torus, and we're looking for functions that in the vertical have 0 vertical mean. So in other words, K3 is not equal to 0. This is all in order to, that the reduction of, or the problem of turning that red vector system into these operators where u and b are given as operators on theta is well defined. We want K3 not equal to 0. Well, this means that d, of course, is not going to equal 0 anywhere. So we have no singularity coming from the denominator. D, of course, is fourth order with respect to K1, K2, and K3, and the numerators are also fourth order. So at first sight, you think, okay, we're dealing with an operator of order 0. But if we look at this a little bit more carefully, it is not an operator of order 0 with respect to the growth in the vector k for all directions in k space. Let's look at M3. So let's consider now we're going to look at a parabolic surface in Fourier space, a parabolic surface where K3 is of order 1, but K1 is of order K2 squared. So in that case, well, when we look at what's happening here, this whole thing is going to be of order magnitude of K squared. This is going to cancel with this term, but this term is going to be behaving like K1. So as we go off to infinity in Fourier space along that parabolic surface, our operator grows, and it grows like the magnitude of K. Well, it grows like the magnitude of K on that surface. So in fact, and the same thing is true if we look at these two components. They grow like K to a power bigger than 0. So we're actually dealing with now a very singular operator. We're dealing with an operator that can be as bad as an operator that is the derivative of a singular integral operator. In terms of function spaces, we're dealing with an operator where u could be in the function space BMO to the minus 1. So BMO, the space of bounded mean oscillation, this is the derivative of a space in that function space, and it could be as bad as that. So we're dealing with distributions. We could be dealing with something that, on the face of it, even if we, so we could start with, well, theta in L2, we could be picking up a very unpleasant looking vector fields. So that's in some sense a major interest that we have in this problem of nonlinear PDE. So here what I've done is I've written down this equation that we call the magnetogeostrophic equation, and I've written down the operators here, setting all these constants to equal 1 for simplicity. But I've retained the constants here. 2 omega, of course, tells us is coming from Coriolis term. This is coming from the ambient underlying magnetic field, whose strength is beta, and eta is the coefficient of magnetic diffusivity, which I gather in the fluid core is expected to be a number that is not very small, a number, let's say, roughly a number that has to be retained. So this is beta squared over eta is not something that is blowing up. So this is the system that we will then be talking about. And so, as I mentioned, some important observations to make about the operator, looking at its symbol. The symbols are even, they're not isotropic, and they're not bounded in all regions of K-space. They're bounded in some regions of K-space, but not all regions of K-space. So if we want to look at the class of functions that we need to be dealing with in analyzing this equation, we basically have to look at classes where the symbol is bounded by K, but could be as bad as that. Well, there's another much more famous equation, at least famous in the mathematical fluid dynamics community, called the surface quasi-geostrophic equation. Again, it's an active scalar equation, has been much studied. There are literally probably hundreds of papers on this interesting equation, and it has a lot of similarities with our mg equation. Here I've written it explicitly, but now the operator that relates u and theta is given here. It's given as the perpendicular gradient of minus the Laplacian to the minus a half. In other words, the operator is just the Riesz transform operator. So this operator is a singular integral operator, but it is not at all as bad as what we have here, because that is an operator of order 0. Here we have an operator that could be the derivative of something like a singular integral operator. Well, I've mentioned just the names of a few people who have worked on the surface quasi-geostrophic equation, and the big challenge, two big challenges. First of all, if we look at the inviscid case, where the viscous parameter labeled nu is equal to 0, is it possible that that equation could actually generate singularities in finite time? Again, many people have looked at it, including some people in the audience, and that question is still open, whether or not it could generate singularities. Now, the viscous problem, which has the appropriate physical viscous term, the physical viscous term for this problem obtained via Ekman-Lair analysis is actually not the Laplacian, but the Laplacian, or minus the Laplacian to the half power. So this problem, which is sort of the physically appropriate problem, and actually also referred to as the critical power, basically the power in which we've got balance between the nonlinearity and the diffusive term, that problem, the question as to whether or not there is global existence or possible singularities, that was answered relatively recently. In fact, there are now 4 different and all very ingenious, interesting proofs of the result for the viscous problem. So when nu is not equal to 0, including a proof of Kiselev, Nazarov, and Wahlberg, and a proof of Caffarelli and Vasseur, which were done at the same time but actually appeared in rather different dates, where they prove global well-posedness of the SQG equation. So that problem, at least in the viscous case, is globally well-posed. What can we say about our problem? Our problem has similarities. Again, here is the mg equation. The operator that we're dealing with it's the derivative. It could be as bad as the derivative of a singular integral called Ron-Zigman operator. The critical SQG equation, we have a singular integral operator to deal with, but there is one common feature of these equations is the relative size of the derivative of the number of derivatives in the nonlinear term and in the diffusive term. For the SQG equation, we've got theta is an operator of order 0, so we have one derivative coming here. We've got one derivative coming from minus the Laplacian to the half power. We've got a balance there. In other words, what we can say is L infinity is the critical Lebesgue space for this problem. And the same thing is true of our diffusive mg equation, because now the appropriate power of the Laplacian that comes from the physical problem, this 3-dimensional problem, is the full Laplacian. So once again, now u written in as an operator of theta there's one derivative there, then there's another derivative in the nonlinearity, and there are 2 derivatives in the diffusive term. So we've got that same balance. And that is in fact what allows us to prove the following theorem, namely that yes, this equation, which on the face of it could be an exceptionally nasty equation because of the possible very bad behavior coming from this operator M is in fact a very nice equation. It's an extremely good equation. So our theorem states that if we start with L2 initial data and kappa is positive, then there exists a unique solution for the MG equation and in fact it's a C infinity solution. So it's a very nice solution. So we'll start off with a distribution theta, calculate U from that distribution. That vector field could be horrible, but as soon as we turn on time and it evolves according to the MG equation, it's going to be, we'll have a C infinity smooth function. So this means that we can sort of start now to ask more questions about the nature of the solutions to this MG equation, knowing now that we're on sort of firm ground. We're dealing, at least in the case where kappa is positive, we're dealing with something that is globally well posed. I won't talk at all about the techniques that we use to prove it, but the techniques are similar to those used by Caffarelli and Vasseur for the SQG equation, and they use De Giorgi. The difficulty is we have to work with U's that could be, as I say, in this very rough function space, BMO to the -1, but and compensation for that, we can work with the full Laplacian rather than the Laplacian to the half power that Caffarelli and Vasseur worked with in the SQG equation. So I will just very briefly touch on some numerical simulations which were not done by me. They were done by Frank Jacobitz, who works with Kai and Marie, and whose work you'll be hearing more about from Kai in the context of turbulence. So this is something I know very little about, so I won't say very much, and I also want to get on in the talk to more results. But if afterwards anyone would like to look at these simulations in more detail or talk about it, I'm very happy to do so. So what we have here is a picture for the MG equation. Again, we know that this C infinity smooth solutions, this is a situation where Frank started with random initial data and then let it evolve. So what t is equal to 0 is actually, in some sense, not 0. T is equal to 0 is where we start the sort of experiment from data that has random data that has already evolved according to this equation, and the equation guarantees smoothness. And so these are the isosurfaces of the scalar field theta, where the iso value is 20 times the root mean square of theta. And now it's 20 in both t is equal to 0 and t is equal to 1. It is 20 times the root mean square of theta. So we're not following a particular packet. We've just got two sort of snapshot pictures. And as you can see, the equation produces certainly structure. The simulations were run without any forcing term, so this means no forcing term. In this equation, where we know this, we've got smooth solutions. The smooth solutions are ultimately going to decay. So, and that decay is illustrated here. And we're certainly seeing in this picture some of the anisotropy in the operators. So isosurfaces of the magnitude of velocity. Here, again, all the parameters were set equal to 1. And what we've got now, again, certainly very strong anisotropy. We've got these sheet-like structures parallel to the axis of rotation, which I gather is rather characteristic of the results from these type of simulations for a rotating fluid. So magnitude of vorticity and magnitude of the magnetic field. So again, this is work in progress. Exactly what all this means is a little unclear. And again, these are only the isosurfaces of the magnitudes of the magnetic field of these vector fields. So these were other initial data. As I say, what I would like to get on to are some further results of the analysis. So what we have proved is that the diffusive equations are globally well posed. What we're interested in, do they in fact produce dynamo action? Well, We know that they produce nice solutions, but will these solutions correspond in any way to growth of the magnetic field? So from that point of view, what we're looking at is a problem of instabilities. Do these equations admit instabilities? Do they admit strong instabilities? And the answer is yes, they do. So we're on good, firm mathematical ground in examining this problem, examining first of all the nonlinear problem via study of the spectrum of the linear problem. We're on good grounds because we know that in fact the problem is globally well posed. So the first result that we prove for this problem is that linear instability implies nonlinear instability. And the proof that we do will work for any problem of this type, namely any problem where we're dealing with u given by m of theta, where that m is the derivative of a singular integral operator. So we consider a steady state. So let theta 0 be an arbitrary steady state, and now consider the perturbation equation. So here we have the linear perturbation equation about this steady state. So we consider this, where the linear operator is the linearized mg operator, and then the nonlinear operator is, as we would expect, u dot grad theta. And then the theorem says that if the linear operator has an eigenvalue with positive real part, then this steady state is Lyapunov non-linearly unstable in any Sobolev space Hs with S bigger than, well, 3 over 2, and so working in three dimensions. The proof of this uses a mild formulation of the description of the solution to the evolution equation. We take a particular initial condition, phi corresponding to the eigenfunction with the eigenvalue with positive real part, and use a bootstrap argument to guarantee that the nonlinear term is going to be controlled on a sufficiently long time to ensure that the linear term actually grows to be, which starts off as order, this term starts off as order epsilon, will grow to be of order 1, of order constant, in a time where this time t sub epsilon, where this constant is independent of epsilon. So the existence of an unstable eigenvalue of the linear problem produces Lyapunov instability. But to conclude that, we need our unstable eigenvalue. So what we now do is we actually construct an unstable eigenvalue for the mg equation linearized about a very special steady state. And we take an extremely simple steady state. We take a steady state that's a function only of the variable x3, that's the variable in the axis, along the axis of rotation, and we take it to be sinusoidal. So periodic, exactly as we want to in the context of our setting. And then we look for a solution to the linearized problem of the following form. Now, since the only coefficients in the linear operator are going to be functions of the variable x3, there's no dependence on x1 and x2, we can look for a solution with any specific dependence of x1 and x2 that we like, and in particular we plug in sine k1 x1, sine k2 x2, and the k1, k2 are arbitrary fixed wave numbers. The x3 dependence we represent as a Fourier series in x3. Substitute that into the linear operator, and we produce this. And this term here is exactly the term that is coming from the M3 component of the symbol for the operator that takes us from theta to u. So that's explicitly sitting here. And now I've actually put back these parameters that are keeping track of where the different, what forces are creating the different terms. This is the omega squared, and this term mu squared is that mu is beta squared over eta, so it's basically the magnetic field parameter. So we have now this Fourier series problem to investigate. And, well, so we rewrite this in a slightly neater notational form. The alpha sub p, rather sigma sub p, is the wave, the frequency sigma that we are trying to construct, modified by the diffusive term. And the alpha sub p is, again, exactly this M3 hat, the symbol corresponding to the third component And actually, for some curious reason, we've written 1 over alpha here. So this is 1 over m3 hat as applied to that particular function. So these parameters, sigma, mu, and kappa, carry the physics of the fluid, and the parameters a and m carry the basic state information. The basic state, remember, amplitude a, sine mx3. So a few things to notice about this parameter, this alpha sub p as a function of p. Well, of course, it's going to, here it behaves like p to the 4th power, so it's going to go to infinity very rapidly, or 1 over alpha p is going to 0 very rapidly, which is a good sign, because what we're, of course, trying to construct from this Fourier series expansion, we're trying to construct a smooth function. And in fact, this very rapid behavior with p is going to allow us to construct a C infinity smooth eigenfunction. Well, now the recurrence relation is equivalent, can be written in this form. We've got a 3-term recurrence relation. We've got something that is not unfamiliar to those of us working in fluid dynamics. And in fact, the first time that this sort of approach was used to construct explicitly an instability in a fluid problem, I think was by Mishalkin and Sinai for the Navier-Stokes shear flow problem in the 1950s. So 3-term recurrence relation, well, that basically calls out for continued fractions. So if we define eta sub p to be these ratios, then we can rewrite this equation as an expression that looks like an infinite continued fraction, and matching it across p is equal to 1, we obtain the characteristic equation that relates the eigenvalue sigma that we're looking for, these frequencies sigma, with the wave numbers that lie inside the parameters alpha. Okay. So we've got an infinite continued fraction. We know that these alphas are going to grow very quickly with the subscript 2, 3, 4, etc. That's good news. What appears on the face of it possibly to be bad news is we've got a continued fraction where the signs now, we've got minus signs here. So the convergence of this continued fraction is not obvious, and it requires some work to prove that these continued fractions actually do converge for sigmas larger than some value. The negative signs that we have here are a reflection in this particular problem of the fact that we're dealing with a Fourier multiplier symbol that is even. If we were dealing with an odd one, we would have pluses. The evenness is reflected in the minus signs that we have here. And those minus signs also are going to give us an interesting feature. So we play around a little bit with the continued fraction. We bound it above and below by a function that is a continuous function of sigma, and show that these f sub p's, with f sub 2 being the term in the characteristic equation, these f sub p's are all smooth functions of sigma for all sigmas, so that sigma 2 alpha 2 is bigger than 2. Namely, that will ensure that this term here is always positive, so we have something there that's real. So these manipulations give us several results. So the characteristic equation is that this term is equal to this. So it's the intersection then of the curve for f2 with the straight line proportional to sigma. We can see that there will be a point of intersection, and let's call that point of at least one point. There may be, in fact, if one was careful, there would be many points of intersection, but we're only concerned with making sure that there is at least one point of intersection. There's one point of intersection that I'll call at sigma star, and at sigma star, using these bounds on the function that's determined from the infinite continued fraction, using those bounds in the characteristic equation, we find that the sigma, which, and remember, sigma sub 1 is sigma together with the diffusive term, sigma sub 2 again with its diffusive term. This thing is bounded, and it's bounded from below and bounded from above. Being bounded from below is what's really interesting to us. Lower bounds in fluid dynamics are not something that one comes up so frequently, and this lower bound is going to be, we think, quite interesting, because we know the alphas quite explicitly in terms of the wave numbers. So we plug that in, and what does that say? Oh, sorry, I've gone in the wrong direction. So now So we've got a lower bound for sigma star. Basically, that's the lower bound for sigma star. We have an upper bound as well, but what's interesting to us at the moment is the lower bound. For that value of sigma star, we put in, now we go back and construct the coefficients in the Fourier series C sub p by the following expressions, and these expressions are used by construction to guarantee that the recurrence relation is satisfied. And for that value of sigma star, we find that the coefficient C sub p as p goes to infinity decay, and they decay extremely rapidly. They decay like basically p factorial to the fourth. So this mechanism has explicitly constructed a C infinity smooth eigenfunction, and that eigenvalue has a bound. The eigenvalue is bounded from below explicitly, and now I've stuck back in the terms for the lower bound. And we weren't very careful about making sure our lower bound was sharp. We plugged in just a large numbers of powers of 2 just to make sure that things were definitely going to be a lower bound. But the important thing of this explicit expression for the lower bound, we feel, is that now it's explicitly given in terms of these horizontal wave numbers and of kappa. So looking at this lower bound, we're most interested in it in the context of the geodynamo. And in the context of the geodynamo, kappa is extremely small. So when this is a small value, kappa is extremely small, we can see what values of K1 and K2 are going to give us a large lower bound in terms of kappa. So that's just straightforward differentiation with respect to K1 and K2 and looking for maxima and minima. And what we find is the following, that when K1 behaves like 1 over kappa and K2 behaves like 1 over kappa to the half power, that will give us a large value of this lower bound. And in fact, what is the large value of the lower bound? It behaves like some constant we could be more careful about, but the important thing as far as we're concerned, it behaves like 1 over kappa. So clearly, when K1 and K2 go to infinity, this term is going to dominate. This term is behaving like K squared. This term can grow at most like K. So we don't have an infinite number of wave numbers that will give rise to this unstable eigenvalue, but we do have, we can choose the K1 and K2, which were completely up to us to choose. We can choose them so that they behave like 1 over kappa and 1 over kappa to the half, and we can obtain this lower bound that behaves like 1 over kappa. So this means that we've got an unstable eigenvalue that behaves like 1 over kappa. Kappa is extremely small in the Earth's fluid core. So this means we've constructed a C infinity smooth, unstable eigenfunction, eigenvalue, with the kappa that grows very, very fast. So in terms of dynamo production, yes, this system does in fact produce dynamo action. It produces an instability, and an instability that grows like 1 over kappa. And that sort of instability, I think, is not an instability that has been previously observed coming from the fluid equations. And that the 1 over kappa is, we wouldn't get a 1 over kappa here if we didn't have that minus sign in the continued fractions, if we weren't dealing with an operator that was an even operator. And just one last minute, since I don't have time to actually go through this, what would happen if kappa equals 0? So if kappa equals 0, well, what's happening from this, just from this statement, it looks as though this lower bound goes to infinity. And in fact, that's true. We can go through the whole process without diffusion, again use continued fractions. We can find a solution that, an eigenvalue that can be as large as we like. So an eigenvalue that can be unboundedly large. And for that reason, we can then prove that the equation, the MG equation, without diffusivity, so when kappa is actually equal to 0, is ill-posed. In fact, it's strongly ill-posed. We prove that this nonlinear problem is Lipschitz ill-posed. So the linear problem doesn't generate a semigroup. The nonlinear problem has this strong ill-posedness to it, even though the problem with kappa, the diffusive problem, is globally well-posed. So just to mention the comment that Idris made this morning in the context of one of these questions. There's a huge difference between Euler and Navier-Stokes. This limit of vanishing viscosity, limit of vanishing diffusivity, is a very singular limit. For Euler, we don't know ill-posedness. For Navier-Stokes, we don't know global well-posedness. But here in this problem, which in some sense is a little bit worse because of the nature of these operators, we have the strong dichotomy, well-posedness when kappa is not equal to 0, and ill-posedness when kappa is equal to 0. So thank you very much for your attention.
Thank you very much. I'm sure there will be some questions.
Can I ask? So maybe some semantic question. You told that from linear instability follows non-linear instability, but I believed that in some sense linear instability study is enough.
No.
Going for
No.
Feynman-Lyapunov theorem.
It's not. It is enough for ODEs. It is not enough for PDEs. In fact, there are some examples of a nonlinear PDE where the nonlinear problem is stable, and yet the linearized operator has an unstable eigenvalue. So it's not enough for PDEs. It needs a proof.
Yes?
If dB dt 0, then how dynamo occurs?
Oh, because here, theta changes with time. So we've got an evolution equation for theta, and B is calculated, B and U are calculated from these operators acting on theta, so they all change with time.
But the original equation in magnetogeostrophic balance, dB dt 0, you get
No, that term has been neglected, not that it's equal to 0. I mean, there are all sorts of terms that were neglected in, and Keith argued why they could be neglected. Not that they're 0. I mean, the partial of U with respect to t is also neglected. That doesn't mean to say that it is equal to 0. It means that this system with the red equations, which will take me a little while, but I can go back and find. Okay. So what's happened is that what we're seeing in these red equations is the dominant balance. It's in no sense saying du by dt and dB by dt are equal to 0. It's saying that those terms are smaller than the dominant balance terms. So we've got dominant balance in the red equation.
Yoshi.
Susan, I'm interested in the effect of rotation.
Yes.
And, so the operator is not symmetric between,
Yes, but
clockwise and anti-clockwise. Yes. But your picture didn't show big difference between,
Oh, well, the picture only showed the curves for positive. They were taking the pictures of the iso value for theta took a positive iso value for theta. If you took a negative iso value for theta, you'd get more curves. So it was just a positive iso value for theta that was the root mean square, 20 times the root mean square. But no, you would get positive and negative if you did it. The pictures need to have a lot more investigation. It's work in progress, as I found talking to a very helpful talk with Marie and Kai yesterday.
One more question, yes.
Do you have any thoughts on what happens when kappa goes to 0?
Well, what happens, that we can prove is the case, is that it's Lipschitz ill-posed. What we guess is the case, in fact, it produces the solution actually produces a singularity. That we can't prove yet. I mean, what we can show is that it cannot be even locally well-posed in any Sobolev space. And for infinitesimal time, it cannot be locally well-posed in Sobolev space. So our guess is, in fact, it's really wild.
If we take the viscous solution and make the viscosity go to 0?
Well, it's a very singular limit.
Yeah, it remains bounded in L2 or...
It will remain bounded in L2, but our guess is that it's going to blow up in some Sobolev norm. But what we prove is that it is Lipschitz ill-posed.
I think we have to come to the end here. Thank you very much again.